Alright, in this video we'll move forward from where we left in video 2. We derived the heat diffusion equation by taking a control volume and by applying the energy balance equation to it. And the heat diffusion equation that we got was 1 upon alpha into the partial derivative of temperature with respect to time, where alpha is the thermal diffusivity. It's K, the thermal conductivity, divided by rho into Cp, equals to the del square T, where del square T is the partial derivative of the temperature with respect to the spatial coordinates x, y, and z, and it's the second order derivative, plus the heat generation term or the volumetric heat generation term divided by the thermal conductivity of the material. So how does this equation look uh, when we expand the del operator? So it looks like this. We have on the right hand side, we have del square T by del x square plus del square T by del y square plus del square T by del z square plus the volumetric heat generation term. This is how the heat diffusion equation will look in 3 dimensions. But if we assume that the system is in steady state, or if a system is in steady state, that will mean that the temperature is not changing with respect to time. So our del T by del T, that is the partial derivative of temperature with respect to time, will be 0. So our left hand side of the heat diffusion equation will be 0, and our temperature will just depend on the x, y, and z coordinates. But what if we have heat transfer in 1 dimension and there is no heat generation term? In that case, our terms with respect to y and z will be 0, because the heat is not being transferred in y and z direction, and there is no heat generation term, so that term goes to 0 as well. So our partial derivatives now are ordinary derivatives, and our equation becomes d of dx into k times the thermal conductivity times the derivative of temperature with respect to x, or whichever direction the heat is flowing in. If it's flowing in y direction, it will be y. If it's flowing in z, these will be z, and the right hand side is 0 uh, because it's steady state. We've seen that Fourier's law, from Fourier's law, our heat flux is qx double prime, which is the heat flux in x direction, equals to minus thermal conductivity times the derivative of temperature, or the change in temperature in x direction. This is what this term means. So if we replace the k dt by dx term by our q double prime x term, we'll get what we'll get is that the derivative of heat flux in x direction with respect to x is 0. Now what that means? It means that there is no change in heat flux in x direction. So the heat flux is constant in the direction of heat transfer. And I'm sorry for this right here. So since the differential equation is a second order differential equation, this equation right here is second order in time, in temperature, I'm sorry. We must have at least 2 boundary conditions to solve for temperature. So in the next slide, we'll see what boundary conditions we can apply. If we did not have steady state scenario, and if we had a del T by del T term on the right hand side, we would also need an initial condition. So If we have a 1D equation and it's a second order ordinary equation, we need two boundary conditions, and if it is not steady state and we have a time dependent term, we need one initial condition. Now let's move on to the boundary conditions and initial conditions that are required. Now we saw that uh, to solve the differential equation that we have, we require boundary conditions and initial conditions. So if our heat diffusion equation is in 3D, we will require 6 boundary conditions, and if it's transient, we'll require one initial condition. And if we have heat flowing in one dimension, we'll need two boundary conditions and one initial condition. But if our problem is steady state, we will not need any initial conditions in that case. So uh, to solve the second order differential equation, there are different types of boundary conditions that you will encounter in different problems, and I'll be explaining each boundary condition here. So there are three different types of boundary conditions that you will encounter, and it depends on what type of problem you're solving. So you need to read the problem and understand what the problem is saying very carefully before you apply these conditions. So let's move forward to the boundary conditions. So this is the equation that we want to solve. It's a second order differential equation. Uh, and to solve for temperature, we need to integrate this equation twice, right? And on integrating this twice, we'll get two constants of integration. So to solve for those constants, we require two boundary conditions. Now, uh, when we integrate this for the first time, what we'll get is that because we have a zero on right hand side, our equation will be uh, thermoconductivity times the change of temperature in x direction equals to a constant, which in this case I have written it as the heat flux in x direction. It could be, you can write this as any arbitrary constant. But if you look at the dimensions of the constant, it will be same as the heat flux. On integrating this equation, what we'll get is that your temperature, that is your T of x, will be the constant of integration divided by a thermoconductivity into x, which is a dependent variable, plus a constant, which in this case I've assumed that the constant is T0. So your unknowns here, so your unknowns in this equation are q double prime x and your T0. So to find the temperature distribution in x direction, you need to know the values of these constants. And how will you get the values of these constants? By applying the appropriate boundary conditions. So as I said, there are three types of boundary conditions that you can have based on the problem that you are solving. So to understand that, let's say this is your boundary right here, and your heat is flowing in the x direction, and this is how I have defined the positive x direction, and at an arbitrary location x and at an time instance t, the temperature is T of x comma t, and this particular location here is x is equal to 0. Okay, so let's see what our first boundary condition is. Our first boundary condition is the constant surface boundary condition. So you will see this as, wait use this pen. So you will see this, or you will write this as t of 0, that is x is equal to 0 at any instant in time, is equal to a constant surface temperature which is known. So this quantity here is known. Okay, so that means that, say, this surface which is at x is equal to 0 is at a temperature Ts. So that's the one boundary condition that you can use. And an example of this boundary condition can be that, say you're solving for a fin, or you're solving the heat transfer between two walls, and you know that the outer surface of the wall is maintained at a constant temperature. So that is your boundary condition. Okay, so let's move on to the next one. The next type of boundary condition you can have is the constant heat flux. So constant heat flux at x is equal to 0. So how will that look like? Now, this particular type has two subtypes. So let's say you have a finite heat flux, that means a non-zero heat flux. So say you have a finite heat flux, and how will you write down the heat flux as? You will write it down as your thermal conductivity times the derivative of temperature at x is equal to 0 is a known finite heat flux Qs. So your second boundary condition will say that your surface here is at a constant heat flux of Q double prime S. What's the second type of constant heat flux? You can have no heat flux here. That means you may have a problem which may say that you have insulation at one end, or one of your walls is adiabatic. Now, what does adiabatic mean? It means there is no heat transfer, or there is no heat flux across that particular boundary. So if you read the words adiabatic or insulated, you will use the boundary condition del T by del X at X is equal to 0 is 0. So there is no temperature difference across that particular boundary, or there is no heat flux across that boundary in that direction, in the X direction. So this is the second type of, these are the two types of the second type of boundary condition that we can have: the finite heat flux and the adiabatic or an insulated wall or boundary. The third type is convection surface condition. Now, for the convection surface condition, your example or your problem may say that uh, your heat is being conducted and one of the surface is losing or gaining heat via convection. So one of your surfaces may be exposed to ambient conditions, and it may exchange heat with the surroundings via convection. So in that case, your boundary condition will look like dt by dx at x is equal to 0, that's the boundary that we are interested in, equals to the Newton's law of cooling, which says h into T infinity, that's the temperature of the surrounding, minus T of that particular surface, that means the temperature at x is equal to 0. So on solving this, you can use this as as one of your boundary conditions, and in this case, say your surface is convecting with some fluid which is at a temperature T infinity and has the heat transfer coefficient of H, and that will be the equation or the boundary condition that you will use. Okay, so please make sure that you understand the different type of boundary conditions and apply them wisely to each problem. We'll also be doing a solved example where we'll see how these boundary conditions are applied in different conditions. So that's it for this video, and please make sure that you go through the solved example as well.